5 brand-new Panther tanks, built in ideal conditions, failed to complete a standard British acceptance trial. This shocking unreliability, observed not once but twice in separate tests, would expose the fatal flaw in German tank design. On the morning of June 12, 1944, at the Fighting Vehicles Proving Establishment in Chertsey, Surrey, British engineers prepared to assess a captured German Panther tank, serial number 21310, built in June 1943 by Maschinenfabrik Niedersachsen-Hannover. This Panther Ausführung D, seized by the Soviets on the Eastern Front, arrived in Britain for detailed analysis. Since 1942, this facility had been the crucible for armored vehicle evaluation, its engineers intimately familiar with the strengths and weaknesses of tanks. But the Panther was different. German newsreels heralded it as invincible, crushing Soviet forces. Wehrmacht training films lauded its technological superiority over any Allied vehicle. Within weeks, British tank crews would confront this very machine in Normandy, making a thorough understanding of its capabilities paramount. On paper, the Panther's specifications were daunting: a combat weight of 45 tons, powered by a 690 horsepower Maybach HL230X engine, governed to 2,500 revolutions per minute for about 600 horsepower in operation, a top road speed of 46 km per hour, 80 mm of frontal armor sloped at 55 degrees, and a 7.5 cm KWK-42 gun boasting a muzzle velocity of 935 meters per second with standard armor-piercing rounds. It appeared a formidable weapon system. Yet, the British test teams were about to uncover a truth German high command already knew but refused to acknowledge: the Panther was a mechanical catastrophe. The British testing regimen was straightforward: subject the Panther to the identical trials used for their own tanks, including cross-country mobility, road speed, suspension evaluation, hill climbing, brake tests, and endurance runs. These were standard procedures, routinely passed by British tanks like the Churchill, Cromwell, and Sherman. What the evaluation team couldn't foresee was that the Panther would never complete the full testing program; it simply wouldn't last long enough. The first issues surfaced during the initial test drives. Drivers reported a complete failure of third gear. The transmission would engage second and fourth, but third gear produced only grinding noises and repeatedly jumped out. The test crew comprised seasoned tank drivers with years in the Royal Tank Regiment, experienced with every British tank and several captured German vehicles. They knew the difference between operator error and mechanical failure. They recognized a truly broken gearbox. This was undeniable: complete mechanical failure. The Panther's 7-speed transmission, featuring 7 forward and 1 reverse gear, was designed for precise speed control. However, its complexity rendered it fragile. Each gear shift demanded meticulous synchronization, every component perfect function. When drivers attempted third gear, something within the gearbox, perhaps a synchromesh ring or sliding collar, had already failed. The gear teeth weren't meshing, the transmission was self-destructing. The evaluation team logged the problem: third gear inoperative. Cause unknown. They pressed on, testing without third gear, as protocols allowed for such workarounds. British tanks had completed trials with single-gear failures before. But they couldn't circumvent what happened next. During rough terrain suspension tests, the Panther exhibited baffling behavior. Its double torsion bar suspension, touted as an advanced feature, felt jarring and uncomfortable. The nose pitched violently over bumps, completely bottoming out the front suspension. Inside, the crew reported being violently jostled, enough to cause bruising. This made no sense to the engineers. The Panther's suspension appeared sophisticated, with dual torsion bars for each of its 18, interleaved road wheels per side, 36 wheels in total, arranged in an intricate pattern. German engineering had supposedly prioritized a smooth ride and excellent weight distribution. Yet, the reality was a suspension system performing worse than the comparatively simple coil spring suspension of British tanks like the Churchill. Instrumentation, including accelerometers and cameras, confirmed the crew's experience. The Panther's suspension had very short travel before bottoming out, hitting its stops with bone-jarring force. The theoretical advantage of the dual torsion bar system, higher loads, better damping, failed to translate into crew comfort or cross-country performance. In contrast, the Churchill 7, with its simpler coil spring suspension and 11 road wheels per side, absorbed the same obstacles with far less violence, providing a comfortable ride. Evaluation team members noted that the Panther's harsh ride would significantly impact crew fatigue in combat. A crew constantly battered by their tank suspension would react slower, shoot less accurately, and be more exhausted after a day's operations. The Panther's uncomfortable ride was a tactical liability, not just a comfort issue. Road speed trials brought further disappointment. While the Panther achieved its claimed 46 km per hour on good roads, its cross-country speed was inferior to the Churchill 7, a heavy infantry tank not designed for speed. The Panther, classified as a medium tank emphasizing mobility, moved like a heavy tank but lacked the heavy tank side and rear armor protection. Then came the first fire on June 14, during hill climbing tests at Farnham Park. British tanks routinely scaled these steep slopes. The Cromwell could sprint up in second gear, the Churchill reliably crawled in first, and the Sherman handled them without issue. The Panther successfully ascended a 40-degree slope. The protocol then required driving back down. As the test driver engaged reverse for a controlled descent, everything went wrong. The engine backfired, not a minor pop, but a massive explosion inside the engine compartment. The sound was like a bomb, powerful enough to partially blow open the engine access hatches, their latches failing against the pressure wave. Fire immediately erupted around the fuel pumps on the front near side corner of the engine bay. Orange flames, distinct from burning wood, shot out, accompanied by thick, toxic black smoke and the acrid stench of burning fuel and hot metal. The driver made an emergency stop, killed the engine, and opened his hatch. The four-man crew, driver, radio operator, gunner, commander, evacuated within 10 seconds. The fire suppression team, armed with Perini extinguishers, rushed forward. 2 men on each side sprayed the chemical agent into the flames. The fire flared briefly, then succumbed to the chemical assault. From ignition to suppression took 30 seconds. Quick response and good training prevented a total loss. Engineers found no serious damage from the explosion itself, major components and the fuel system were intact, and the engine could still run. However, such a powerful backfire, capable of blowing open hatches and starting fires, was deeply concerning. Engineers noted the Maybach engine's high compression ratio made it susceptible to catastrophic backfires, a fundamental problem in its architecture. They repaired the damage and continued testing. The Panther had to be fully evaluated, British tank crews would face these machines in combat within weeks, with the Normandy landings imminent. The War Office needed comprehensive data on the Panther's capabilities and vulnerabilities. On June 14, the evaluation team conducted pitch and roll tests, driving the Panther over ramps and obstacles at various speeds, 10, 15, 20 miles per hour, with a turret-mounted camera recording its movements. This assessed suspension performance and crew comfort during tactical maneuvers. The Panther's results were contradictory. Camera data showed the suspension damped oscillations quickly, faster than British tanks. Yet, every team member who rode the Panther cross-country reported an uncomfortably harsh, stiff, unyielding ride. This contradiction suggested the Panther's suspension was optimized for measurements that looked good on paper, but failed to deliver actual crew comfort or operational effectiveness. The second fire erupted on July 28 during endurance trials in Long Valley. The protocol involved repeated circuits of a test course to assess mechanical reliability under sustained operation. The Panther completed one full circuit. On the second lap, the steering required adjustment, a standard procedure. The driver halted the tank and switched off the engine. Immediately, thick smoke filled the turret, originating from the engine compartment. Within seconds, an explosion ripped through the engine bay, igniting the engine compartment floor. Flames spread rapidly. This fire was more severe than the first. The entire engine compartment was engulfed before the crew could react, forcing immediate evacuation. The fire suppression team rushed in, but the blaze was too extensive. The Maybach engine burned intensely, melting fuel lines, igniting hydraulic fluid, and warping metal components. By the time it was extinguished, the Panther's engine compartment was destroyed beyond economical repair. Engineers meticulously examined the wreckage. The official report detailed their findings. Another backfire had started the fire, this one occurring after the engine was switched off. Some incandescent material, likely carbon buildup on spark plugs or a glowing carbon piece in the combustion chamber, ignited fuel vapors. The backfire expelled fuel and oil vapor through the oil bath air cleaners, which were centrally mounted on the engine with inlets underneath. This sprayed oil and fuel vapor directly onto hot valve covers and exhaust manifolds. With the engine hot from operation, the vapor ignited instantly. The ensuing explosion ruptured flexible fuel lines, pouring burning fuel into the compartment. The Panther had literally burned itself out from the inside. Trials on this machine were abandoned. The Fighting Vehicles Proving Establishment issued their damning report in May 1944, though testing had concluded in late July. The Panther compared very unfavorably with any British tank in service. The mechanical trouble experienced during these limited trials was severe. Third gear failed immediately, the suspension performed poorly despite impressive specifications, and the engine was prone to catastrophic fires. Many test results were inconclusive because the tank failed mechanically before the full evaluation could be completed. Official report FT 1391 became a critical intelligence document circulated to British tank units preparing for Normandy. The report highlighted specific comparisons. Cross-country, the Panther's average speed was less than that of the Churchill 7, despite the Panther being classified as a medium tank against the Churchill's heavy tank designation. On roads, its maximum speed was verified at approximately 30 miles per hour, matching German claims. But reliability was the critical finding. the amount of mechanical trouble experienced on this trial suggested the Panther compared very unfavorably with any British tank now in service. Regarding suspension, while camera pitch records showed good oscillation damping, all evaluation staff members who rode cross-country found the ride harsh, uncomfortable, and a contributor to crew fatigue. The British evaluation of German Panthers was far from over. The experience with that first Soviet-captured Panther in the summer of 1944 would be dramatically amplified 3 years later, with consequences that would definitively expose the myth of German technical superiority in tank design. The war ended in May 1945. As British forces advanced into Germany, they seized vast quantities of German equipment. In Hanover, captured by the British Ninth Army in April 1945, one of the 3 major Panther assembly plants was discovered, the Maschinenfabrik Niedersachsen-Hannover (MNH) facility, which had been building Panthers since early 1943. Allied bombing raids in mid-March 1945 had partially destroyed the assembly lines, but significant numbers of Panther components remained: engines, transmissions, hull sections, turrets, gun systems, all awaiting assembly. British occupation forces included the 823 Armoured Troops Workshop of the Royal Electrical and Mechanical Engineers, REM, a unit specializing in armored vehicle repair and maintenance. Arriving in Hanover on June 8, 1945, they initially set up operations at the Hanomag factory. Their commanding officer, Captain William J. Hadlow, received orders from British Army of the Rhine headquarters to complete as many Panther tanks as possible from the remaining MNH components. The objective was clear: the British needed Panthers for comparative testing against their own designs, such as the upcoming Centurion and the experimental Black Prince heavy tank, to fully understand the Panther's true capabilities. The 823 workshop relocated to a largely intact sub-assembly plant in Lärtzen, south of Hanover, on June 29, 1945. The main MNH assembly line at Linden was too heavily damaged. Lärtzen, which had produced track links, gun tubes, and smaller Panther components during the war, offered good lighting, a functioning roof, and adequate workspace. Captain Hadlow, a skilled REM officer, systematically organized the assembly. German workers who had built Panthers during the war were retained, their intimate knowledge of the tank systems invaluable. Many were ambivalent about helping their former enemies, but practical considerations, jobs, money, food for their families, overcame national pride. The British paid them in occupation marks and provided rations. British REM mechanics supervised the assembly, learning German engineering philosophy firsthand. British tanks were designed for field maintenance with basic tools, components were accessible, replaceable, and often interchangeable. German tanks, particularly the Panther, were engineered like precision machines, with tight tolerances, complex system interactions, and specialized tool requirements. Proper Panther maintenance demanded resources and expertise unavailable in combat. It was an assembly plant tank, not a field maintenance tank. The assembly team followed original German quality control procedures. Each chassis underwent a 15-kilometer test drive without the turret to verify engine, transmission, steering, track tension, and suspension. After mounting the multi-ton turret with an overhead crane, the complete tank endured another 50 to 60 kilometers of driving. These were the standard German acceptance protocols used by MNH during wartime. The finished Panthers were tested on the nearby heathland around Lärtzen by REM drivers, with German mechanics providing guidance. Even these brand new Panthers, meticulously assembled under ideal conditions with quality components, quickly developed problems. Oil leaks appeared around valve covers, coolant leaks from engine seals, and steering became progressively stiffer as clutches wore. These new tanks, in their initial break-in period, were already exhibiting significant maintenance issues. The work spanned 9 months, from August 1945 to spring 1946. The 823 workshop completed 9 Panther tanks and 12 Jag Panthers, the tank destroyer variant. Each vehicle received a small brass plaque on its front glassy plate, identifying it as, assembled by 823 Armored Workshop Rhein, Army of the Rhine at MNH Hanover. These were brand new Panthers, built to wartime specifications under British supervision, serving as permanent documentation of this unique operation. In late 1947, the fighting vehicles proving establishment at Chertsey received 5 of these vehicles for comprehensive testing, 2 Panther tanks, 2 Jag Panthers, and 1 Burge Panther armored recovery vehicle. The ambitious plan was to subject all 3 Panther variants to the complete British acceptance trial program. Every test a new British tank had to pass. The trials would provide definitive data on how the Panther compared to British armour in cross-country mobility, road performance, hill climbing, endurance, reliability, and more. Finally, the British would possess comprehensive scientific data on the tank German propaganda had portrayed as invincible. Testing commenced in February 1948. The vehicles were loaded to full combat weight with ballast to simulate ammunition, fuel, and crew equipment. The Panther tanks weighed 44.5 tons, Jag Panthers 46 tons, and the Burge Panther 42.5 tons. All 5 vehicles were essentially new. The Panthers and Jag Panthers had minimal running time since their 1945 assembly. The Burge Panther, however, had accrued 632 kilometers and required a new engine before trials could begin. Crucially, no spare parts were available beyond spare engines. The vehicles had to complete trials using only their original components. Within days, it became clear that completing the full test program would be impossible. The Panthers were failing mechanically at an alarming rate. Steering mechanisms malfunctioned, engines caught fire, and transmissions broke down. The test team, led by engineers from the Fighting Vehicle Design Department, quickly modified their approach. The original plan to test all 3 variants separately was abandoned. Instead, they would extract whatever data they could from any operational vehicle, cannibalizing broken ones for parts to keep others running. The first major failure occurred during initial cross-country trials. One Panther tank suffered a complete steering mechanism failure. The Panther's steering system utilized clutch and brake steering. To turn left, the driver disengaged power to the left track and applied a brake to slow it, pivoting the tank. This worked acceptably on flat ground at moderate speeds. But under stress, on rough terrain, making sharp turns, the system failed catastrophically. The test driver attempted a sharp left turn across a rutted section. He engaged the left steering clutch and applied the left brake. The clutch slipped. Instead of disengaging smoothly, it burned. Overheated friction material produced smoke from the clutch housing. The steering became erratic. The driver tried to compensate, but the clutch was destroyed. With the left side steering inoperative, the tank could only turn right, making proper control impossible. The driver halted the Panther, reported the failure, and the tank was immediately withdrawn and stripped for parts. Examination of the destroyed clutch assembly revealed burned friction surfaces from excessive load. This was a design inadequacy, not a manufacturing defect. The clutch was not adequately sized for the loads generated by the Panther's weight during hard steering maneuvers. The second Panther tank developed engine problems almost immediately. During cross-country running, the Maybach engine began overheating. Temperature gauges climbed into the red zone, exceeding 100 degrees Celsius. The driver noted warning indicators and reduced speed, but the temperature continued to rise. Something in the complex cooling system was malfunctioning. The Panther's sealed engine compartment, originally designed for amphibious capability, though never implemented, posed cooling challenges. Air intake and exhaust required intricate ducting, and coolant circulated through radiators integrated into the air intake. Any restriction in airflow or blockage in coolant passages would rapidly overheat the engine. The driver continued the test run as protocol dictated, despite high temperatures, but not yet critical levels. Then came the familiar pattern British engineers had seen 3 years earlier: the engine backfired. A sharp bang, like a shotgun blast, reverberated inside the engine compartment. Explosion, then fire erupted immediately. Orange flames were visible through the engine deck grills, and thick black smoke poured out. The driver shut down the engine and evacuated. The fire suppression team rushed in, but this blaze was more severe than the 1944 incident. Flames had spread to multiple fuel lines, and the heat was intense. Extinguishers couldn't suppress it completely. By the time the fire was brought under control, the engine was destroyed, melted valve covers, burned through fuel lines, incinerated wiring harness, and a damaged carburetor. The Maybach HL230 engine, thousands of Reichsmarks to manufacture, was now scrap metal. This Panther was also withdrawn, designated a spare parts source. Its transmission, steering clutches, road wheels, anything salvageable, went into inventory to keep other Panthers running. The first Jag Panther lasted longer, but not by much. It completed several test runs successfully, inspiring hope that at least one vehicle might yield useful data. Then, during an endurance run, the transmission failed catastrophically. Gears stripped inside the gearbox, and the vehicle lost all forward drive capability. It was towed back for cannibalization. Internal examination showed gear teeth had broken under load, indicating the transmission components were insufficiently robust for the vehicle's weight and sustained operational stress. The second Jag Panther became the primary test vehicle by default, the last one still mobile. The team focused all efforts on keeping it operational, completing some mobility tests and road speed runs. But the Jag Panther rapidly deteriorated. Steering became increasingly difficult, the transmission made concerning grinding noises during shifts and clanking sounds during hard maneuvering. The engine consumed oil at an alarming rate, requiring top-ups after every test run. During hill climbing trials, disaster struck. The protocol included brake-holding tests on steep slopes, critical for evaluating a tank's ability to hold position during combat, essential for defensive hold-down operations. The Jag Panther was driven to the top of slope number 4, a 35% grade, steep enough to be impassable for most wheeled vehicles. The tracked Jag Panther ascended successfully, its Maybach engine steadily pulling the 46-ton vehicle. At the summit, the driver positioned the vehicle nose up on the slope and applied the brakes. The protocol required holding stationary for 30 seconds, then releasing and driving over the crest. A simple test, routinely performed by British tanks. The driver applied the brakes, the Jag Panther held for perhaps 5 seconds. Then the brakes failed. The driver felt a sudden loss of resistance through the pedal as it went to the floor. The Jag Panther began rolling backward down the slope. 46 tons of steel and armor, accelerating in reverse down a 35% grade with no brakes. The driver attempted to steer and control the descent, but the vehicle gathered speed. The steering responded sluggishly at first, then not at all. The Jag Panther rolled faster, building momentum with each meter of descent. At the base of the slope was a large oak stump, perhaps half a meter high, remaining from land clearing years prior. The Jag Panther struck the stump at approximately 25 km/h. The collision was violent, shaking the entire vehicle. The crew was thrown forward against their restraints, and metal screamed as the hull hit the immovable obstacle. The impact broke a torsion bar, one of the massive steel bars supporting the road wheels and providing suspension. The broken torsion bar, under tremendous spring tension, punched through the side wall of the gearbox like a spear through armor. The transmission housing was breached, transmission oil poured out, and gears inside were knocked out of alignment. The transmission was destroyed. The last functional vehicle was now disabled beyond repair with available resources. The crew evacuated, shaken but physically uninjured. The Jag Panther sat immobile at the base of the slope, leaking transmission oil. Engineers confirmed the torsion bar's penetration of the gearbox housing. With no spare gearboxes, the vehicle was irreparable without factory-level resources. The Burj Panther, the armored recovery vehicle, was pressed into service for testing, despite not being a combat tank. The team attempted the 25-mile cross-country endurance trial with it. Partway through, the Burj Panther's gearbox failed. With no spare parts, no operational vehicles remaining, and all test vehicles either destroyed by fire or mechanical failure, the trials were permanently suspended. The Fighting Vehicle Design Department issued their final report in February 1948, brief and blunt in its conclusions. Owing to the inherent unreliability of the steering mechanism and the proclivity of the engine to catch fire, it had been impractical to cover the full trials program. The original intention of testing all 3 Panther variants had been abandoned early. The tests were incomplete because all available vehicles were put out of action by major mechanical failures. Very little information of any value was obtained from the trials. The reason for this failure was the general mechanical unreliability of the Panther and Jag Panther tanks. The report concluded with a stark recommendation: close this project. Further testing would serve no purpose. There were no more serviceable vehicles, no spare parts, and the tested vehicles had demonstrated such poor reliability that additional data would not change the fundamental conclusion. The contrast between German propaganda and British testing reality was absolute. German newsreels showed Panthers as invincible, technical documentation portrayed them as sophisticated and advanced, Wehrmacht training materials emphasized their superiority. Yet, when British engineers subjected these tanks to the same routine tests that British tanks passed regularly, every single Panther failed catastrophically. Not one completed the standard acceptance trials. 5 vehicles tested, 5 vehicles destroyed or disabled by mechanical failure, 0 successful completions. What British test teams discovered through two separate evaluation programs, the 1944 testing of the Soviet-provided Panther and the 1947–48 testing of the reassembled Panthers, was a fundamental flaw in German tank design philosophy. The Germans prioritized impressive paper specifications, thick armor, extreme angles, high-velocity guns, advanced suspension, sophisticated engineering. But they failed to ensure these components could work reliably in the field, neglected maintainability, ease of repair, and operation by average crews under combat stress. The Panther was rushed into production in 1943 to meet Adolf Hitler's deadline for the Kursk offensive, Operation Citadel, in July 1943. Design finalized in January 1942, testing was cut short, problems glossed over, and production began before the design was mature. The result was catastrophic. Early production Panthers at Kursk in July 1943 were mechanical disasters, with breakdown rates exceeding combat losses. On July 5, 1943, the first day of the offensive, only 40 Panthers remained operational by evening, the rest had broken down. Transmissions failed, final drives broke, engines overheated and caught fire, steering systems failed. Panthers burned spontaneously without enemy fire. German command at Kursk filed detailed reports. General Heinz Guderian, Inspector General of Armoured Troops, observed Panthers firsthand and recommended halting production until fundamental problems were resolved. His recommendation was ignored. Germany desperately needed tanks, Eastern Front losses were unsustainable. Production couldn't stop for refinements. Instead, incremental improvements were made while production continued, accepting high mechanical failure rates. Later production models, the Ausführung A, September 1943, and Ausführung G, Spring 1944, received modifications, but these addressed symptoms, not fundamental design problems. The Panther's Maybach HL230 engine, designed for 30 to 35-ton vehicles, continuously ran 30% above its designed load in the 45-ton Panther. This caused overheating, excessive fuel consumption, backfires, and engine fires throughout the war. The transmission and final drive were similarly overstressed, designed for lighter loads, leading to rapid wear and frequent failure under the Panther's combat weight. German field reports from Normandy in June 1944 noted Panther engines typically lasted 1,400 to 1,500 kilometers before needing major overhaul or replacement, but final drives failed much sooner, often after just a few hundred kilometers. German tank units constantly cannibalized disabled Panthers to keep others operational. Reports repeatedly stated Panthers had to be kept running through intensive maintenance, not that they ran reliably. The clutch handbrake steering system was inadequate for the Panther's weight, clutches wore quickly, slipping or burning out under heavy strain during sharp turns or difficult terrain, exactly as British testers observed in 1948. The Panther Crew Manual, published July 1, 1944, warned against torturing the steering system, stating it would break the engine quickly, and that those who do this have no sense of tanks at all. This was not the language of a manual for a reliable, well-engineered vehicle, but for a fragile one requiring careful handling to avoid catastrophic failure. The engine fires that destroyed the British Test Panther in July 1944 and multiple Panthers during the 1948 trials were not anomalous, they were systemic problems documented throughout German service. German combat reports from 1944 to 45 repeatedly mentioned Panthers catching fire. A June 28, 1944, report from General Heinz Guderian, shortly after D-Day, stated, "Der Panther brennt so ordentlich schnell, the Panther burns so terribly fast." German commanders knew since Kursk in July 1943 that Panthers had a severe fire risk, but the fundamental engine design problems were never adequately resolved. The causes were precisely those identified by British engineers: backfires igniting carburetor overflow, oil leaks from valve covers dripping onto hot exhaust manifolds, and defective fuel pump seals creating gasoline pools. A March 1944 German report described carburetor overflow wetting spark plugs, discharging unburnt fuel through exhaust header gaskets, causing fires on the outside of the motor. When British engineers examined their burn test Panther in July 1944, they documented the exact same failure mechanism German engineers had identified months earlier. The problem was known, it was not fixed. British tank crews who captured and attempted to use Panthers against German forces experienced these reliability problems firsthand. The most famous example was a Panther Ausführung D, Cuckoo, captured by the 4th Battalion Coldstream Guards in Holland in autumn 1944. Abandoned by its German crew due to a transmission fault, British tankers found it intact, started its engine, and decided to press it into service. Cuckoo received large white Allied recognition stars and a volunteer crew. Photographed extensively, including in action against Geister and Kassel on the Maas River on November 29, 1944, Cuckoo initially impressed British crews with its powerful and accurate 7.5 cm KWK-42 gun, superior to Churchill guns, and its superb Zeiss optical sights. Its thick frontal armor provided confidence against German anti-tank guns. Cuckoo participated in several engagements over nearly 3 months. When it worked, it was formidable. Its gun could destroy German tanks at ranges where German guns couldn't penetrate its frontal armor, and its optics allowed precise long-distance engagements. But Cuckoo demanded constant maintenance. The engine continuously leaked oil, fuel consumption was enormous, and steering needed frequent adjustment. The transmission, the supposed reason for its abandonment, remained problematic, making grinding noises and metallic clanking during hard maneuvering. British mechanics constantly worked on Cuckoo between operations. After almost 3 months, mechanical failure, not enemy action, ended its service. Historical sources differ on whether the final failure was the fuel pump system or transmission, but all agree it was a breakdown. No spare parts were available, German components weren't interchangeable with British, and no German logistics chain existed. Cuckoo was withdrawn. The Coldstream Guards returned to their slower, less well-armed, but vastly more reliable Churchills and Cromwells. A Churchill might not penetrate a Panther frontally, but it would still be running at the end of a week of continuous operations, while the Panther would likely be broken down, awaiting parts and specialized maintenance. The French Army had a similar post-war experience, operating captured Panthers in occupied Germany through the late 1940s. French maintenance reports documented constant mechanical problems, engine failures requiring replacement, transmission breakdowns, steering malfunctions, and final drive failures. The French ultimately abandoned captured Panthers due to unsustainable maintenance requirements. Despite access to German spare parts and experienced German mechanics, they couldn't keep these tanks reliably operational. By 1950, France phased out captured German tanks entirely, favoring American Shermans and French-designed vehicles, despite the Panther's paper superiority in firepower and armor protection. All these experiences, British tests in 1944 and 1947–48, German combat reports from Kursk to the war's end, and Allied attempts to operate captured Panthers, revealed a consistent pattern. The Panther tank was a maintenance-intensive, mechanically unreliable vehicle requiring exceptional care and immediate spare parts. In controlled factory conditions with skilled mechanics and full parts availability, a Panther could function adequately for limited periods. But in actual combat conditions, with field maintenance, limited spares, and average crews under stress, Panthers constantly broke down. The statistics were undeniable. British testing provided invaluable intelligence. Allied tank crews facing Panthers knew not to be intimidated by its reputation. Yes, it had thick frontal armor and a powerful gun, but it was mechanically fragile. Combat tactics evolved to exploit these weaknesses, force Panthers into situations requiring mechanical stress, make them maneuver in difficult terrain, climb hills, reverse rapidly, and fight in close terrain where their range advantage was negated. The Panthers' mechanical weaknesses became tactical vulnerabilities, informing Allied combat doctrine. British tank tactics in Northwest Europe specifically exploited Panther unreliability, force engagements into close terrain, keep them moving and maneuvering until something broke. A disabled Panther was as combat ineffective as a destroyed one, and Panthers regularly disabled themselves without being hit. German reports noted many Panthers abandoned on the battlefield had no combat damage, only mechanical failures irreparable in the field. The story of British Panther evaluation is ultimately about the difference between engineering for specifications and engineering for reliability. Germans created a tank that looked impressive in technical documents and propaganda: thick armor, powerful gun, sophisticated suspension, advanced optics. The British created tanks that worked. German Panthers had better frontal armor, higher muzzle velocity guns, and superior paper specifications in nearly every category. British Churchills, Cromwells, and American Shermans had comparatively mediocre armor, guns, and unimpressive specifications. But Allied tanks kept running. They could be maintained in the field by average mechanics with basic tools, didn't spontaneously catch fire from design flaws, completed their missions, and returned for the next operation. The 5 Panthers tested at Chertsey from February to mid-1948, all brand new, built under ideal conditions with quality German components and skilled assembly, could not complete a standard acceptance trial. Every single one failed mechanically before finishing the test program. One burned completely, one suffered catastrophic steering clutch failure, one had transmission gears strip under load, and one had its gearbox destroyed when a broken torsion bar punched through the housing after brake failure on a slope. The 5th was cannibalized for parts before it could even be tested because the others failed so quickly. This fact, documented in official British Army reports, represents the final verdict on the Panther tank as a complete weapon system. It was not the wonder weapon of German propaganda. It was a mechanical disaster that consumed German resources, industrial capacity, skilled labor, and strategic materials while providing unreliable combat capability. The Panther required 2 to 3 times as many man-hours to build as a Panzer IV, used scarce alloy metals Germany was running short of by 1944, and demanded highly skilled crews and mechanics. Yet, it broke down more frequently than simpler German tanks, and far more frequently than Allied tanks. From a strategic perspective, Germany would have been better served building more Panzer IVs, which were reliable, easy to maintain, and effective, rather than pursuing the technically sophisticated but fundamentally flawed Panther design. The myth of German technical superiority in tank design died in the engine compartment and transmission failures documented by British test engineers at Chertsey in 1944 and again in 1948. The tests were methodical, scientific, and conclusive. The results were unambiguous. The Panther looked formidable, had impressive specifications, and German propaganda portrayed it as invincible. But when subjected to the same standard tests that British tanks passed routinely, it failed completely, not once, but twice, in separate test programs 3 years apart, using different vehicles from different sources. The conclusion was inescapable and corroborated by German combat reports from their own frontline units: the Panther was unreliable, prone to catastrophic mechanical failure, difficult to maintain, and unsuited for sustained combat operations. The men who fought against America left the most honest record of its power. Battlescars brings you one of those stories every single day. If this one held you to the end, subscribe, tomorrow's story is already waiting. And your next one is right here.